Hello everyone, welcome back to Alkaline Hydroxide 784 and honestly let me just tell you I just recorded the audio for the maths one because if I must do all these at one go instead of like spacing it out, because if I space it out then I will forget to do it and then I won't have time to do it, so yeah. I hope I don't talk for 30 minutes this time. Okay, so welcome to the physics series. We are today covering our second episode, which is kinematics. So, luckily, kinematics isn't too long. I hope. I mean, I talk 30 minutes just for measurements. Yeah. So I'll try to be a bit more succinct or like a bit less really like I don't know wishy-washy about it. I don't think that's the right term. Okay, never mind. Let's start. So for kinematics, well, it is one of the topics that you learned in O levels as well. So by right, you should be decently good at it by now, or not. I'm pretty sure you are. Okay, just kidding. I mean, for me, in my physics isn't exactly my strongest subject. It is. I prefer maths and chemistry. But and for some reason I had trouble with kinematics and dynamics at the beginning of the JC of JC. So but towards A levels I was actually pretty decent at it, so yeah, I guess it's not such a bad thing. Yeah, let's just start. uh so in kinematics we look at rectilinear motion and non-linear motion. Okay, never mind about it. It just means you go straight or you don't go straight. Logic. Okay. Uh, candidates should be able to define and use displacement, blah blah blah. Okay, so as usual, I'm looking at the learning outcomes. I do not know why I read that out. Okay. So the first point is about the usual terms of displacement, speed, velocity, acceleration. So can I trust you all to actually know the definitions of all this? Okay, I mean I'm just gonna cover it really quickly. So displacement is the distance between your starting point and your ending point, your point of origin and your current point. And it also comes with your this direction in the sense, so it's either negative or positive based on your point of reference. Okay, so for speed, your speed is, well, the amount of distance that you cover over the amount of time that you take to cover it. That's the average. If you use instantaneous speed, you can use your dx, sorry, yeah, differentiation to find it, which would be something like what, dx or dt or something. Yeah. Then velocity would be, instead of using x, you use s, which is displacement. Displacement for some reason correlates to s, maybe because it has the letter s in it somewhere. So velocity would be the total change in displacement or the total change in time, or if you're using instantaneous, it would be ds over dt. And acceleration would then be dv or dt, or if you have your total change in velocity or total change in time, yeah, based on which one you're going on. And of course, if you go backwards, velocity is the integration of a over t, sorry, a with regards to t, like integration a dt. And then displacement in turn would be integration of v d, like integration v dt. Yeah, that's basically what it is. I think you have the exact phrasing in your notes, so just use that. Don't trust me. I may not use the correct phrasing, I don't know. But I think it's generally how it goes. That's the definition. Okay, so the second point is using graphical methods to represent distance, displacement, speed, velocity, and acceleration. Okay, so since you all know maths, I hope. If you do not know, you can look at my math series. If you already know maths and calculus, especially, because this is basically calculus. If it isn't, then I don't know. I have nothing to say. So distance and displacement. Of course, distance is the scalar, displacement is the vector. Simple as that. Speed and velocity. Speed is the scalar, velocity is a vector. And acceleration is a vector because there isn't a scalar representation of acceleration. Okay, so the best way to think about it is use calculus. You don't have to do calculus, you don't have to do your maths equations there, but you think about it in a calculus way. So your displacement, when you convert it to velocity, you try to find the gradient of the displacement. So if your gradient is positive, you put positive. If your gradient is negative, you put negative. And if you want to think of a step further and see how the velocity graph looks, then think even more about how the gradient changes. Does the gradient change from a negative gradient to a positive gradient? Does it change from a positive to a negative? Does it change from negative to 0, positive to 0? And then use that to draw your velocity graph. And likewise, you can do velocity to acceleration. And when you're translating it backwards from acceleration to velocity, use the area under the graph. So if you look at how much area is there under the graph, whether it's increasing with as the graph progresses, whether it's decreasing or what is going on. Of course, technically it should always be increasing, right? But if the graph goes below the x-axis, it actually decreases the area. So the area below the x-axis will be negative area and the area above is positive. So take that into consideration when you're converting it back in terms of integration. Yeah, so just use the calculus and do it. I'll probably, if I had enough time to draw all the different graphs, I can draw it. I think if you have trouble with this, you can PM me, like ask me whether this curved graph becomes this or what. I guess it's a bit confusing, but hopefully you'll be able to do it if you think about it in a calculus standpoint. Okay, so usually a question will ask you, will show you maybe the displacement graph and then ask you to convert it to velocity and acceleration at the same time. So yeah, just do that. Okay. I need more water. Okay, anyway, the third point is identify and use the physical quantities from the gradients of blah 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 blah. Oh, okay. This one is just asking you, it's just, you should be able to read the graph. That's the point. Okay, so in terms of gradients, you can use your ruler and then find out use your gradient formula and just find the gradient, I guess. Nothing crazy about that. And of course the area, for area you can just use your triangle equation or something, or if it really does require calculus, then just use your calculus. Haha. Okay, just kidding. Most of the time you just need to do some triangles and rectangles. That's good enough, because usually they'll just give you this graph that has like a bunch of squares on it, then they ask you to find a certain value, like for example acceleration. Maybe you get a VT graph and you need to find A. You just count the number of squares and write it down. They don't expect you to do you don't need to do calculus. just count the number of squares. You get the answer. Okay, so the next point is derived from the definitions of velocity and acceleration equations that represent uniformly accelerated motion. Actually, yeah, this should be easy enough. You just need to first start with what is the definition of velocity and acceleration, which I have told not very long ago. For velocity, you just put speed final, sorry, not speed final, sorry, displacement final minus displacement initial, or change in time, I guess. And your acceleration in turn would be something like what, v minus u over t, time taken. Yeah, you'll use time as the total time taken, because you start at time 0, so you don't really need to worry too much about final time and starting time. And from there you can then do those, those equations that are in your data, the formula sheet. You just need to make those equations out of this. So if it's easier to see it in terms of a graph, because you're looking at uniformly accelerated motion in a straight line, which means your graph will be a very nice, like it looks like those xy graph, x equals to y kind of graph. So you just use a triangle and you get your equations, and then from there you can derive the other equations. It's just a bit of algebra actually. I just realized this is mostly maths. Oh well. How come I'm good at maths but not good at physics? Okay, never mind. I question myself many times why I'm like this. Okay. No, actually, it's in physics. It's not really the equations that are the problem. It's remembering them that's the problem. Remembering which one to use, and maybe definitions as well. Definitions, and sometimes I just make a lot of careless mistakes, as I always do. So yeah, I guess that's my problem. Okay. Yeah. So I would have probably written it down by now. Okay. So the next point is solving problems using equations, which represent uniformly accelerated motion. Oh yeah. So you have those equations. So it's in your your formula sheet, or whatever you call it, that page with all the formulas. I'm pretty sure that there's at least one or two of them in there, and the others you can just remember it. It's not that hard to remember. So you just remember it and then use it for situations where there's only uniformly accelerated motion. Do not use it for a question that uses ununiform acceleration, or some some weird motion that's not even straight. You cannot use it for your circular motion, for example. So yeah, just take note of that. And of course, the most useful example that we can use these equations for is an assumed uniform gravitational field without air resistance, and you have something falling through that particular field or space. If there's no air resistance, then your acceleration is constant. So yeah, you can use these equations. It is a bit sneaky. To be honest, sometimes science just involves a lot of simplifications that you make your life easier, and you make things a bit easier to calculate. Because in reality, like you know, I guess it kind of applies to your life also. In reality, everything is complicated. There's too much of complexity in the world, such that it might be quite hard to find each and every bit of detail or information about the world. And that's why we have people to simplify things, or to make it more succinct, concise to understand. And yeah, that's just how science works. um, of course, we also try to make it to look at it in its complex state as well. But to begin with, you start with the simplified version of it, and then you move towards the more complicated version. Okay, so the final one is describing, sorry, not final one, the second final one. Describing qualitatively the motion of bodies falling in a uniform gravitational field with air resistance. I think for this, just look at your notes, honestly, because even if I say it, it won't be entirely correct, or it may not be the right phrasing. But I'll just tell it to you very quickly. So, okay, let's just have a very interesting scenario of someone throwing a ball from from some helicopter 1,000 meters above the ground, maybe. Like, yeah, 1 kilometer above the ground. Wait, I don't think there's helicopters 1 kilometer above the ground. That's a little bit too low, is it? I don't know. Anyways, so the ball is falling, and yeah, usually they use those people who to go, what is it called, skydiving. Yeah, skydiving people. No, I'll just use the ball. Okay, so the ball at the very very beginning, at time is equals to 0. Its acceleration is g, which is 9.81. Even that isn't the true value of g, because g probably has like a gazillion decimal places. Yeah, exactly. Science just simplifies a lot of things. In order to make our lives easier and make our calculations easier, and also because in a way trying to use the exact value may not be that useful for us. It's not going to make much of a difference. But anyway, so this ball starts with the acceleration of g, because that is the calculated g that you get when you use your gravitation equations, if you know what I'm talking about. um yeah, so if you have your g, your ball is starting at g, and as it moves down and down, through the air, it experiences air resistance, because it's moving through the air, obviously, to experience air resistance. And with that, there'll be a decrease in acceleration, because you know that the ball has a force downwards, which is its weight, and now it has another force going upwards, which is the air resistance. And in this scenario, since your net force is now lesser than mg, your acceleration will also be lesser than g, so its acceleration decreases. And at the point of time, it will decrease so much until the acceleration becomes zero, and its velocity is therefore constant. And when its velocity is constant, it will just be going at free fall. Sorry, is it free fall or something? I don't know. It'll be going at its, what's that thing called? What's that? See, I told you, I had trouble remembering terms like these. Yeah. Yeah, it's going at its what's that thing called? What velocity is that? Free fall velocity. Sorry. Yeah, so it'll be going at a constant velocity when both the forces are equal. And that's basically that. Oh, terminal velocity, yes, terminal velocity. That was what I was talking about. Yeah, so it reaches terminal velocity, and it will be falling at that velocity thereafter. Yeah. Until you do something to it, I guess. Okay, so the last point is about explaining the motion due to a uniform velocity in one direction and uniform acceleration in a perpendicular direction. Oh yes, this circular motion. Yeah, is it it's kind of circular motion. Because if you think about it, if your velocity is going straight, but your acceleration is towards your right, for example, then you're being pulled constantly towards the right. So even as you go straight, you will not be going straight. You'll be going in a circle. If you think about it, imagine like you know, your you have like a pin at the center, and you have a string tied to it, and you have a ball. So when the ball is being pushed around, your string, which is your acceleration, thus your string will represent that acceleration pulling you inwards, and your ball cannot keep on going straight, because it's attached to a string. It has an acceleration in that direction, and therefore it will keep going in a circle, kind of, until it runs out of, until the air resistance stops it, in a way. Yeah, so I will explain this in greater detail in the actual topic of circular motion, but that's basically how it works. So yay, it's not 30 minutes long. I can now finish this. Yeah, actually I'm tired. Actually, which topic is circular motion? Wait, there isn't a topic for that? Oh no. Wait, am I? Uh, Wait, but I had an entire topic on that. Where is it? Wait, there's no topic for circular motion. uh, Wait, oh yes, that's the sixth one. So motion in a circle. I'll cover more on that later. Okay, so I hope you enjoyed this, or at least found it useful enough for your own needs. Maybe you're writing notes and you don't know what to write about, so yeah, you can use this as a reference. If you found this useful, please press the like button and subscribe. And with that, I would like to say thank you and bye. Next episode is dynamics, by the way.